The demands on data rate are continuously increasing in cable-based as well as wireless networks. Particularly in industrial wireless LAN networks, these demands are associated with extensive technical innovations. So far, comparably simple technologies such as the intelligent antenna drive diversity was sufficient to guarantee reliable and fast data transfer. In order to achieve data rates beyond the current boundaries, new methods had to be developed first that made a significant increase of the data rates possible. The high data rates of the 802.11n standard are mainly achieved with the following methods. Method 1. MIMO. The MIMO technology offers the greatest contribution to the fast 802.11n communication. The MIMO technology is mainly based on the parallel transmitting of several data streams. Per data stream, one antenna pair is used. This means one antenna at the transmitter and one at the receiver. These data streams all simultaneously use the same radio channel in full bandwidth. The distinction of different data streams is achieved by phase shift and the different polarization of the radio signals. On the receiver side, MIMO furthermore uses the different signal propagation times and polarization changes by reflection of the surrounding space. The antennas have a special role here. They should always have the right distance to each other. Receive combining enables the repeated combination of the receiving signals on individual antennas. This is particularly intelligent signal processing. Per data stream, a data rate of up to 150 megabit per second can be achieved. The 802.11n standard provides up to 4 parallel data streams. However, in practice, 3 data streams and thus a data rate of 450 megabit per second has been tried and tested. Method 2. Channel bundling. The 802.11 standards so far provide a channel width of 20 MHz. The 802.11n standard combines these channels to one, with more than double the width. Channel bundling works particularly well in the 5 GHz band, since it is considerably wider than the 2.4 GHz band and provides non-overlapping channels. Method 3. Short guard interval. A transmitter that works according to the old 802.11 standard waits for an interval of 800 nanoseconds after transmitting a packet before it transmits the next packet. 802.11n can halve this waiting time to 400 nanoseconds with the MIMO technology. The data throughput improves by approximately 10% due to the shorter waiting time. Method 4. Packet aggregation. Apart from the user data, each packet always also includes control data, for example, the receiver's address data. If this address data is the same for several consecutive packets, the packets can be grouped together and transferred in one piece. The multiple transmission of the control data is thus not necessary and bandwidth is saved. Finally, the technical data. Together, the explained and some other methods achieve an improvement of the gross data rate by more than a factor of 10. This results, therefore, in a theoretical gross data rate of 450 megabit per second for 3 data streams used. After all, in practice, the net data rate clearly exceeds the data rate of fast Ethernet. To be able to fully use the available data rate, the cable-based infrastructure behind the 802.11n network has to be a gigabit Ethernet. 802.11n is fully downward compatible to the previous 802.11 standards.